This conference will now be recorded.
Okay, so welcome everybody to my presentation. As Richard has kindly introduced me, I'm Mohamed Wehbi. I'm technical director at GeoBear. Previously, I used to be part of part of Network Rail and the Trackbed team. And I just have to say, it's such a great pleasure to come and present to the Birmingham section. I always used to attend and present in the Birmingham section when I used to be part of Network Rail. So it's great to be, back to this forum. It almost feels like home. So the presentation will be about the use. Will be about mainly about the use of geopolymer technology on the railway infrastructures. Okay. So just to give you a brief introduction to who we are, GeoBear is a global leader in non-disruptive solutions. The business was initially established in Finland in the early 80s, and the UK part of the business was then later established in the early 90s. We've got multiple offices across the UK, and we've done more than 200,000 projects worldwide. We've got international outreach, so we've got multiple offices and branches worldwide in the US, Sweden, Finland, and Poland, and China. And we do work in a number of different sectors, including highways, commercial, residentials, utilities, airports, and more recently on the railways. Just to give you also another introduction to geopolymers, and just to give you a taste of what geopolymers are really about. So let's start first by defining what are geopolymers. Geopolymers are expandable resins that can be injected into the ground using special equipments for the purpose of void filling, but also for the purpose of soil stabilization. Okay, and I always like to show a video of the geopolymer just to give you a perspective on what the material really looks like. And this is a video just shows the geopolymer as it gets injected into a void, and in a matter of a few minutes or seconds, it will expand and fill the void and hardens. Okay. Geopolymers have a number of properties. One of the most important properties of geopolymers is the ability for it to expand. Depending on the type of geopolymers, geopolymers can expand up to 40 times their original volume, generating different amount of lifting pressures. Now, depending on the type of application that we want to use the geopolymer for, we select the right type of the geopolymer for the application. Geopolymers are also, depending again on the type of geopolymers have good structural properties. So geopolymers can have a compressive strength up to 7 MPa and a tensile strength of up to 6 MPa. As you may notice from these measurements, geopolymers are kind of good in both compression and tension. So they're unlike concrete or grout. Concrete is really good at compression, but quite weak in tension. But geopolymers are good in both of these aspects. Also, another important property of geopolymers is that geopolymers have, again, depending on the type of the geopolymer, geopolymers can have a stiffness modulus somewhere between 10 MPa all the way to 90 MPa. Yes, it is true geopolymers can have quite high compressive strength, but at the same time, they've got the geopolymer composition is not too stiff in that sense. It has a stiffness range similar to natural soils. Okay. Also, furthermore, geopolymers also have great ability to resist fatigue damage under cyclic loading. So if you take a sample of a geopolymer and you start applying cyclic loading, which is what you normally get under railway loading, the geopolymers would have a very high fatigue life. So it will take quite a while for it to actually start creeping and cracking. If you compare, for example, the geopolymer performance, fatigue performance to typical engineering fields like a Type-1 material, geopolymers can last up to 120, 140 years under fatigue loading. But Type-1 material, for example, the best Type-1 material that you can ever source probably will last you around 70 years. So it's quite superior from that point of view. Furthermore, geopolymer properties, there are other important geopolymer properties. For example, geopolymers can harden rapidly, so it only takes a few minutes or seconds for it to expand, hardens, and cure. Geopolymers are also water-free solutions, so they do not require water to initiate the curing and hardening process. They are also environmentally friendly materials, so the molecular structure of geopolymers is quite stable. We've actually done some quite extensive testing on that from the environmental point of view to understand, whether it's going to leach into water or contaminate or aquifers or all that. So what we found out that geopolymers are quite benign in that sense, so they do not contaminate waters or aquifers and the soil as well. They're also a lightweight fill material, so they're about 10 times lighter than conventional concrete and 5 times lighter than conventional grouting. Okay. Now, what are the different applications of geopolymers in the railways? Well, there are a number of ways, there are a number of applications. I've kind of tried to, highlight some of the most relevant ones to this forum. So the first application is the use of geopolymers in void filling. So especially under slab tracks. Under dynamic loading, slab tracks can develop some voiding under the slabs. And this is due to subbase erosion. The erosion is as a result of soft underlying conditions combined with poor drainage. And as a result of these voids, you can develop some structural cracks within the slab, resulting in poor track geometry and track performance. Now, this is one of the most important applications, I think, in my view, because a lot of misconception about slab tracks is that slab tracks will last you forever. But the ugly reality is nothing lasts forever. Everything is in a constant state of deterioration. So it will eventually deteriorate. And the problem with slab tracks is like quite hard to fix, or to restore the geometry. It's not like ballasted tracks where you can just go in and start tamping and restore your track geometry. That's not something that you can really do with slab tracks. Some slab track systems do have some, some mechanisms that allows you to lift a little bit the track, but they're quite limited. What we can do with that, we can basically, if we know the locations of the voids, that could be via site investigation or geophysics investigation, we can then drill into these voids and basically insert a 12 millimeter diameter tubes into these slabs to basically start injecting geopolymers into these voids. The geopolymers will basically start filling those voids, and also if there's any water there, it will start pushing that water away from the void and fill the void completely. We can actually keep injecting geopolymers to the point that we can actually start generating high lifting pressures, and these lifting pressures will actually start lifting the slab, and we can control that lifting by ensuring that, by using laser level monitoring, for example, you can lift it to the desired position. So it's not only you're filling the voids, but also you will have the ability to lift the slab to the desired position and restore your track geometry. Some obvious applications, another obvious applications of geopolymers. Well, we can use geopolymers to treat sinkholes. Sinkholes on the railways is quite a rare occurrence. It doesn't really occur that often, but when it occurs, it can occur due to a number of reasons. For example, the presence of dissolution features, the collapse of culverts, water leakage, or even seawater erosion. And you can end up with a quite difficult sinkhole to treat. What we can do about this? Well, basically we can start injecting the geopolymers into the sinkhole cavity to kind of fill the geopolymer the sinkhole cavity to fill it completely. The advantage of using this technique is that, first of all, it's going to expand and cure very quickly. So it's not like, if you fill it with grout, you're going to have to wait for a few days to get the full strength. With this, you'll get this full strength in a matter of a few hours max, and then you can open your line back to traffic. The other advantage in this is that you're not going to be using as much quantity as you would have used in conventional grouting, because geopolymers can expand, and because of that, you can actually use much less quantity of material. And the other important advantage, which I haven't listed in this slide, is that the fact you're not introducing water to the system. So imagine if you've got, I don't know, some chalk layer, for example, underneath that's driving the sinkhole. Well, the last thing you want to do is introducing water to the system. So geopolymers do not require water in that sense, so you're not going to be adding water to the system. Okay. Another important application and I think it's again another very important application is the use of geopolymers to strengthen formations or subgrades. Now, so far I've spoken about the use of geopolymers to fill voids, but you can also directly inject geopolymers into ground. Now, the question that may arise to some of you is like, how are you going to inject geopolymers, for example, in almost an impermeable soil like clay? how there's nothing to fill there, how you can do that? Well, when we inject the geopolymers into, for example, cohesive soils like clay, what we tend to create is something called like we create some sort of root lenses, and these root lenses will spread into the clay via something called hydraulic fracturing. So when we eject, we'll hydraulically fracture this clay, and then the geopolymer will start spreading into these fractures, creating root-like lenses. These root-like lenses, they can actually reinforce the soil. They will almost act like the reinforcement in the reinforced concrete. They'll basically reinforce the soil, and also confine the soil, so you'll get much more or higher strength out of the soil because of that. Okay, and this is how some of these lenses would look like in 3 dimensions. You can see we've done some excavation trials recently, and where we actually looked at what sort of patterns we're getting here, and you can see the plates, these sort of lenses, and this is how they look like: reinforcing plates. They're quite thin plates spread into the clay, and these what would actually strengthen your soil. We've done some testing in Austria where we had a testing pit, and we filled that testing pit with some really soft soils. And what we've done, we basically measured the modulus of the soil using the LWD. I'm sure some of you are familiar with this machine. We measured this modulus of that soil before the injections, and then we measured the soil modulus after the injections. So before the injections, the soil modulus was around 4 MPa, so very soft stuff. So if you've got that under the railways, the design will be a challenge, I can assure you of that. But after the injections, we can see that the geopolymer have managed to increase the soil modulus by almost a factor of 3. And we can really, we can even go beyond that by injecting even more material to get the design strength. So this all comes out of the design. But you can see here from this experiment where geopolymers does indeed increase the strength and modulus of the cohesive soils. However, in granular soils, the mechanism is quite completely different. In granular soils, what happens is that when you inject geopolymers in granular soils, let's say some sort of fill material that is quite loose, what happens, you tend to create these sort of bulbs. And these bulbs will have a diameter somewhere between 0.4 to 0.6 of a meter. And what these bulbs will do, they will basically expand and start compacting all the soil around it. And as a result, you will basically increase your compaction and your relative density, and therefore you'll end up with higher strength. And this is, the process, how, the stages of this process. You start injecting, and the geopolymer will start filling some void or creating some sort of a small bubble with no expansion. As soon as the expansion starts, it will start pushing all the material around it, creating some sort of a plastification zone. And that plastification zone will basically increase your relative density on compaction of that soil around the bubble. And you can inject in patterns to ensure that you get to get the desired strength that you want. Now, how this can be used? Well, as some of you already know, when we try to design a railway track bed, for example, we always try to design the track bed thickness in such a way that we can, we have enough thickness that we protect the subgrade adequately. The ugly reality is, in many instances, we're not really able to do that. I remember in a number of instances when I was a railway designer, I couldn't do that because of a number of reasons. For example, you can have undetected soft spots. Well, we simply do not, the site investigation will never capture everything. We take a sample every 100 meter or every 50 meter, but you're not going to know everywhere. You're not going to know the soil condition everywhere. And as a result, you're bound to miss some soft spots. So you're going to end up with an under design. Also, budget constraints. Sometimes we simply don't have the money to actually build a full track bed thickness. That's as simple as that. Also, you may have the budget and you may have sufficient ground investigation, but you've got a nearby foundation or a structure that if you actually install a deep track bed design, you're going to undermine the nearby foundation. Therefore, you cannot really install a full track bed depth. And as a result, what happens is that you end up with high stress concentrations on the subgrade, resulting in deformations, settlements, and also differential settlements affecting your track quality. What can we do about this? Well, again, we can actually inject the geopolymers into into the soil, into the subgrade soil, basically reinforcing the subgrade strength and basically reducing the levels of deterioration. How can you use this? Well, we can use it in two ways. You can, for example, utilize this methodology when you're coming to renew tracks. So if your track life has expired and you're coming to renew it, and you somehow have a soft spot or a soft subgrade underneath, you would require a thicker excavation. And with geopolymers, you can reduce that. For example, if you've got a subgrade modulus of 4 MPa, let's say, according to network rail standards, if you want to renew it and you've got a line that is less than 100 miles an hour, you would need 450 mil of type 1 plus 300 mil of ballast. That's the conventional standardized design. However, if you decide to actually use geopolymers just before the renewal, for example, you can actually inject the geopolymers in this sort of manner with a certain quantity, and you can actually reduce the thickness of the type 1 requirement from 450 mil to 150 mil. So therefore, you have actually saved on the excavation. So you don't have to do excavations and deep excavation, and as a result, you're going to save on logistics, spoil removal, and all that. So and also consequently your carbon footprint, because you're not going to require the same amount of possession as well on this one, and logistics. So that's one way of using it. The other way of using this is, for example, to use this approach as a maintenance methodology. For example, let's say you've got a railway track already built on a soft subgrade, and it has this kind of typical design: 300 mil ballast plus 100 mil of type 1 or sand blanket. Okay. Now we know that this is not really the ideal design for this kind of subgrade, but your track components are still new; they're not old. So your sleepers are not very old. The rails are still okay. So, and your ballast is still okay, but you've got a soft subgrade, and as a result of that, you're losing your track geometry. Well, what you can do, instead of waiting for the renewal and keep tamping until you get to the renewal, you can actually use the geopolymer stabilization method to actually start strengthening the subgrade and reducing that level of deterioration, hence reducing your maintenance. Just to give you an example, I've done some analytical modeling on how the track geometry would respond to such a railway track, for example. And I've looked at 30 years, for example, life of the track. If you've got a track, a track built on a soft subgrade that has a modulus of 4 MPa at 100 miles an hour or less, you're going to end up with quite a poor track quality, and your track is going to keep deteriorating. And this graph shows the track quality versus time. So that's the equivalent of the CCQ on network rail. So that's your standard deviation charts. And you can see that in many instances, you're going to have to tamp quite frequently. However, you can come in, instead of midlife, for example, instead of keep damping and waiting for the track to kind of reach its end of life completely, you can actually come in and actually intervene and inject the geopolymer and stabilize the track and reduce the rate of the degradation. So here, just to show you two graphs where the track quality time history before and after the stabilization, supposedly that you decided to go with the geopolymer stabilization after 10 years of operation. So after 10 years, you decided to intervene with geopolymers. What happens? And this is the area, this is here that shows, so before the intervention, obviously the track will deteriorate the same. But after we intervene, you can see there's a significant reduction in the rate of deterioration. And as a result, you're going to reduce the amount of tamping cycles that you have. Okay. Just to give you a brief summary, so if you don't inject, for example, in the first 10 years, you're going to have to tamp 17 times, and in the last 20 years, you're going to have to tamp 12 times. And obviously, you haven't done any cost saving or asset life extension, and your renewal requirement is quite high. You still need the 300 mil ballast plus 450 mil of type 1. However, if you decide to carry out the injections after 10 years of operations, in the first 10 years, you have 17 tamping cycles. But in the last 20 years, after you intervened, you've actually reduced the tamping cycles from 12 to only 7. And that will translate into roughly 20% saving in maintenance costs. And also, because you've reduced the rate of degradation, you've extended the life of the asset by 5 to 7 years. But also, your subgrade is still good, so it's still strong because you treated it with the geopolymer. So your maintenance requirement has actually gone down as well. So from 450 mil of type 1, you would only need 150 mil. So you saved on maintenance, you've extended the life of the asset, but also you've reduced the requirement for future renewals. So you're winning in three fronts here. Okay. We can use this technology to also treat discrete soft spots, for example. So if you've got a soft spot somewhere in the middle of the track, quite discrete, small, you can actually go in and start injecting it in this sort of approach where you inject a very strong geopolymer into the subgrade, into the soft area, and then start ramping out the treatment so you can create a nice ramp to the treatment. And this is how you can treat soft spots. We can also use this technology not just under the railways. We can use this technology to treat, for example, structures nearby the railway. So if you've got an OLE, for example, foundation nearby, and they're suffering from severe settlements, you can actually treat that as well with a geopolymer as well. So you don't have to, excavate deeply. Now, the solutions that I've just described to you are quite applicable and useful in cohesive soils and on granular soils. But when we start talking about peat, now peat is a very difficult material to engineer for. So it's quite hard to design anything that would actually stand against the presence of peat in your subgrade. And many often you end up with, no matter how good your design is or how thick your trap bed design is, you end up with quite problems. And I dealt with some of these sites during my time in Network, so they're really hard to deal with. And roughly, whenever you've got peat, the typical engineering solution in civil engineering, for example, it's either to excavate the peat, get rid of the peat somehow, and sometimes this is not really an option, especially if the peat layer is too deep or too thick. Or the other option is to actually use some sort of a piling system, a micropile, for example, under the track, or other types of piling systems. Okay. What we have is another solution that would deal with peat. For example, we can inject geopolymers into specially made geotextile sacks. And these sacks, as you start injecting into them, they will start expanding and create almost like a pillar, a pile, a structure that looks like a pile in that sense. And it will have a diameter of roughly up to 400 mil. And you can inject or install these geopolymer pillars between the sleeper cribs, for example, to almost create almost like a foundation through the peat, and those geopolymer pillars, what they will do, they will basically transfer all the stresses from the track and then depositing these stresses into a stiff competent layer. So basically bypassing all the load from the peat to the stiff competent layer. We will have to do a 40 mil diameter drill in this case. And the installation is completely in situ, so you're not taking any track out or anything. We can just do it between the sleeper cribs and with the right depth to actually ensure that we create a sufficient arching effect, okay, that will transfer the load efficiently. And this is how they look like, how these geopillars would look like when they first install them, and they will expand and create these sort of firm, solid pillars. Okay, we've done some testing on these in Finland, and we've actually we managed to quantify the bearing capacity of these pillars. These pillars will have a bearing capacity of around 200 kilonewtons, so quite a strong structure, really, and would comply with most structural requirements in civil engineering practice. Okay. Another application, where we can use this technology is to stabilize embankments. Now, on railways, our embankments are built almost 100 years ago. They're made of poorly compacted materials with inadequate drainage and poor vegetation management. And we end up with a lot of issues on these embankments, which sometimes in certain instances we end up with catastrophic failure and maybe even some derailments as a result of that. What we can do, well, most embankment failures are associated with some sort of a slope instability. You can get, crest failure or slope failure or shoulder failure, and you can also get some shrink and swell effects. there, but they're mainly associated with the slope, generally speaking. Okay. So what can we do about that? Well, we can actually inject the geopolymers into the slope of these embankments to kind of stitch the embankment slope and increase the shear strength and cohesion of the embankment if you've got, let's say, clay embankment. And you can actually improve the factor of safety of the embankment using this technology. And again, you're not excavating, you're not taking anything out. If there's sufficient access from the outside, in theory, you don't even have to stop your railways. We can carry out the work as everything, as long as you're not getting to the track support zone or too close to the track, you can actually carry out the work on the outside. And this is here just to show you an example of a recent work that we're currently working on in Poland, where there was an embankment that had an unstable slope, and you can see a massive tension crack next to that embankment as a result of that failure. And this is the sort of treatment plan that we've kind of developed for this particular site. Our company also have a dedicated engineering department. So we've got our own internal design house, so we can carry out some extensive modeling and to even quantify what sort of factor of improvement you will get as a result of the injections. So on this particular case, on the Polish embankment, the embankment had a factor of safety of about 0.8. And after the injections, we're actually predicting that the factor of safety will go all the way to 1.4. So that gets it into an acceptable safety level. Okay. Another application of this technology is on transition zones. So as some of you may know, when you have an abrupt variation in track support, if you're moving from a plain line track built on a subgrade to a track built on a bridge, let's say, for example, you can have some significant maintenance problems on that as a result of the transition zone, especially if you're traveling at high speeds. When this happens, because of this differential support, you're going to end up with differential settlement, and that differential settlement will cause voiding, and you're going to start damaging your rails. You're going to increase your dynamic loads, and you get some ballast attrition as a result of the dynamic loads, all sort of problems. Now, how to treat this? Now, unfortunately, in the UK, we don't really have a clear standard that tells you how to design a transition zone. Okay, there's, you can look in the trumpet standards in the UK, and none will tell you exactly how to build a proper transition zone. Now, across the continent, there are some advices from the UIC that tells you, what sort of transition zone that you need to build. But these designs are quite difficult to implement on a UK railway environment, and they're mainly associated with very deep excavations using many types of materials. It's not easy to build, and probably none of the RAMs would accept, the associated costs. It's quite difficult to do, especially if you tell them to excavate quite deeply next to a bridge abutment, for example. No one is going to like that. So there's no real solution for this. But what we can do with this technology, we can actually inject the geopolymer in a gradual manner. So almost create a gradual strengthening as we're getting closer to the bridge, increase the strengthening as we're getting to the bridge, creating almost like a transition zone to the bridge. And that transition zone will basically, mitigate any sort of the effects of differential settlement and high dynamic loading. And this is all can be done in situ without really taking the track out, and you're creating a very nice transition in situ. So you don't have to do any excavation with this, and that will help you create a smooth transition to the bridge. The final application that I decided to put here is the use of geopolymers as a mean to mitigate vibrations, ground-borne vibrations. Now, ground-borne vibrations is a bit of a mystery, honestly. It's not something you can easily predict or mitigate. It's quite difficult, especially when you've got nearby residents, for example, residential housing, and you've got a railway line. If you've got certain characteristics of the track and the soil underneath, you can actually generate quite high vibration levels into the nearby residential housing, which can impose some safety concerns into these structures. Now, what we can do about this? Well, we can actually, there are a number of research that have actually shown that you can use geopolymers where in such a way that you can create almost like a thin barrier between the track substructure and the nearby housing. And these thin barriers will almost act like dampeners, and they will basically dissipate the vibrations transmitted to the houses, okay, nearby houses. I've actually read some interesting article published in Canada where it shows that they've done some experiments on this and where they've measured the vibrations at different distances. And what they've done, they created an open trench. Now, an open trench obviously is one of the most effective ways to kill vibration transmissions, but it's not something that anyone likes because that trench will be filled with water. It can be a safety hazard issue. There are many issues with that. So that's obviously a very effective way of doing it. But also what you can do, you can create that trench, but then fill that trench with a geopolymer. Now, geopolymers, when they expand, they create these sort of bubbles, air bubbles inside them, and these bubbles will basically act like almost like a shock absorber. So they will absorb all the energy from the vibrations transmitted. And here, just that article actually showed the effect of what happens to the vibrations under these conditions, and you can see there's a significant reduction in the vibration levels as opposed to if you don't have any trench. So obviously it's not as good as the open trench, but it actually does reduce your vibration. That reduction can reach up to levels up to 60% reduction in the vibration levels or transmission of these vibrations. And this is the article is available, anyone can read it. So it's quite an interesting article to read. So, and this can be easily done. You just need to excavate a trench, 25 centimeter wide, and we can put the right type of geopolymer that would actually tackle the right type of vibrations, because it's quite important to understand what type of geopolymer you need to use in this particular application, because different geopolymers will behave differently and will have different damping characteristics. So it's quite crucial to understand this. Okay. Now moving on to case study. I've decided to pick some case studies from previous work that we've done in the UK and outside the UK to show this the application of this technology. Now, one of the famous examples is Kentish Town slab track. Now, I'm sure a lot of you are famous with this slab track. So the Kentish Town slab track was built, I think, around the 70s. And at that time, the design, I think, was not really. I don't think the design was a very robust design. But what has happened is that the slab track started to deteriorate due to soft underlying conditions and poor drainage, and this resulted in poor track geometry, poor top, and some track faults as a result of that. So that was around 2016 when we used to be called Eurotech at that time. And for this particular job, we were called in to carry out the stabilisation solution and lift the track as well to the right geometry, as a temporary solution. So it was just as on the temporary basis to just install this solution. So until they give them, which will give enough time for the maintainer to actually come back and then take out the slab track and install a brand new ballasted track at that location. I think this section has already been renewed there. And this was part of a civils work package as well. So what we've done, we've carried out the injections at an interval of 1.5 meter. So the spacing between them was around 1.5 meters, and we inject the material at 1.5 meter below the ground level. And this is where they had the soft clay and the soft material. And we've also monitored the lifting process to ensure that we've kind of lifted the track to the desired position. Okay. I think the client or the asset owner of that particular track section carried out some deflection monitoring using high-speed cameras, and they've measured the deflection levels, vertical deflection measures of the track under dynamic loading before and after the geopolymer treatment. And before the treatment, the geopolymer, before the treatment, the track was deflecting by almost 6.5 mil. Now, to the people who are familiar with this topic, 6.5 mil under a slab track is a ridiculous amount of deflection. You shouldn't really get that. The ideal level that you really want to achieve on any track really is around 2 to 3 mil max. of vertical deflection. But here in this instance, we were getting about 6.5 mil of track deflection. And this is just a video to show how the track was behaving under dynamic loading when it wasn't stabilized. And you can see the massive vertical deflections due to voiding and material washout and poor track performance. And this is a video showing, again, the next part of the video showing the track in the stabilized case where the track stopped moving, and we managed to reduce the deflections to almost 2 mil, just almost on the perfect optimum range of track deflection. Okay. You can take that measurement and do some back engineering calculations to quantify what has happened. Well, we've managed to reduce the track deflection by about 69%, and we've reduced rail bending stresses by 26%. And we've also, you can use that measurement and you can manipulate that measurement to calculate what sort of track vibration levels reduction that you've ended up with. And we managed to actually reduce the track vibration levels by up to 50%. Okay. You can also look at the track geometry, what has happened to the track geometry. And here I've looked at the track geometry recordings for twist faults, vertical fault, and dip angles. And the dashed area represents the area where is the section of interest, and you can see there's a significant track geometry or poor track geometry performance in these areas. You've got high twist faults, high top, and also some dip angles. And after the stabilization, we looked at the runs after the stabilization, and you can see there's a significant improvement in the track quality, and to the point that we almost eliminated the dip angles from that track. Okay. Another example that we've recently finished is a track bed stabilization work we've done in Poland. A railway embankment near, around this, I can't pronounce the village name, so apologies for that, but it's around the central part of Poland. And that embankment was suffering from significant settlements and ballast loss. And this was due to main two reasons. There was soft underlying conditions, so the clay was there was clay there and it was quite soft. And there was also some, to make things worse, there was animal borrowing as well. So some animals were digging around underneath the embankment. As a result of this, there was a significant loss of track geometry, high track deflection, shoulder loss, voiding, and even to the point that they started seeing some localized sinkholes. Okay, and this is just a video to show how the track was performing before this stabilization. And you can see how the track was deflecting quite high, at a high level, at very, very low speeds. And obviously the maintainer there didn't like that, and they wanted to do something about it, but without taking out the track. So what we've done, we basically carried out our stabilization work into the embankment and the subgrade itself. So we didn't touch the ballast. So the ballast stayed intact, the track stayed there, nothing was taken out. And what we've done, we basically drilled into that into the embankment and the subgrade, and we carried out intense amount of injections into that embankment. And you can actually, if you look close to that picture, you can see the injection tubes are getting prepared, and they've already been installed, and they're getting prepared for us to actually come in and connect our injection guns to it and basically stabilize the subgrade. Okay. We've installed about 880 injection points at a distance of 54 meters, and you can see here the green zone. The green zone has basically this is where we've got the most severe type of problems, and we create almost like a step change in the treatment, so we don't create any sort of localized transition zones or localized hard spots into this. To validate the effectiveness of the treatment, we carried out dynamic probing there on that in two locations on that site. So here it shows these two graphs shows the results before and after the injections. So the red bars represents the dynamic probing blow count before the injections. And you can see here that all the red bars. And the blue bars represents the dynamic probing blow count after the injections. And you can see it in both samples, and you can see there's a significant increase of blow count after the injections, reaching almost 6 times increase, and that would obviously translate into higher shear strength and higher track stiffness there. Okay. Another example that we've done, I think, a few years ago on Burma Road, slab track in Glasgow. I think that particular site was experiencing significant settlements. So I think these settlements were almost reaching up to 150 mil dips. As a result of that, a speed restriction was imposed to 5 miles an hour until they fixed the dip, basically. So we were called into site and we carried out the stabilisation, where we actually injected into the ground, into the granular material under the ground, and also to strengthen it, but also to lift the track to the desired position. We completed the work within 2 separate shifts over a single 24-hour possession. And we also carried out dynamic probing before and after the stabilisation work. And these are 3 different locations where we've done the testing, and you can see there's a significant increase before and after the stabilization in terms of the blow count, and that increase ranged somewhere from 50% all the way to 100% increase in the number of blow counts. Okay. The final example is on a platform, on a work that we've done on a rail depot in Farnham rail depot. The track was out of tolerance due to poorly compacted fill and localized cohesive soils and water ingress issues and increase in loading. So what we were tasked to do was to actually carry out injections to kind of restore the geometry of that platform. And I think the picture tells you everything. The picture on the top right hand side of the slide, you can see the geometry of that platform before the stabilization work or the lifting work in this instance. And after that, the picture below that shows the final results, basically, after we finished the work. And it's interesting to note that the depot remained operational throughout the entire work, so we didn't really disturb the work there. I always like to actually look at these pictures. Quite fascinating, I think, in my view. And I think that concludes my presentation. Thank you all, and I hope you find it interesting. Please, if you've got any questions, do not hesitate to contact me.
Thank you, Mohamed. That was really interesting, and I think you showed quite a few use cases there that I think will be useful throughout the network and elsewhere, really. And yeah, very interesting. Just before we move on to the questions in the chat, and if anybody does want to ask any questions, there's the speech bubble icon on the top right. Feel free to type into there. Just before we move on, I've actually got a question. So looking through it and some of the use cases in soft soils and track stabilizations, there's quite a lot of parallels there between that and what we have done in the past with micropiling. How does it stack up in terms of strength and cost versus a micropile solution?
Oh, okay. So in terms of the cost, let's start with the cost. I think that's the most important aspect. In terms of the cost, it's quite difficult to pin a certain figure for this, because it depends on what sort of bearing capacity that you're trying to achieve, the soil conditions and all that. So the quantity and the amount of geopolymers that we're going to be using is going to be different. Even the type of geopolymer will be different. So depending on what's the design, so it's quite hard to ping a particular figure. But I'll tell you what's interesting about this is that at least from my previous experience with micropiling, as you know, I've worked quite extensively on this. Micropiles, I think, would typically have a diameter, I think, reaching up to 250 mil. 200 to 250 mil the cap size of that, and it's because it's limited to the size of to the sleeper crib spacing, so you can't really put a very large micropile, and because of that, so your micropile diameter is quite limited. You can't really go beyond 250, I think. And what we here have is something that is actually have technically a bigger cap. So therefore, you'll be able to create a better load transfer as a result of that, because it's bigger. So you might be able to use actually less piles if you need to, or or even have better performance, because the pile cap is actually larger, 100 mil larger. So your arching effect will be much more effective than what you would get from a typical micropiles. Micropiling is a good solution. Obviously, it's not something, but obviously we're talking about peat engineering. Engineering in peat is a challenge, I have to admit. So you can see there's quite a resemblance, obviously, but they're two different systems, have different advantages, I think, in that sense.
Okay, that's good. So if we move on to the questions in the chat, the first question in there from Philip is around asking for your contact details. I don't know if you want to pass those on at some point.
Definitely. I'll share those just before the end of the session.
Excellent. And then a question from Rob. Does the use of the product in track soft subgrade increase the requirements for track drain?
Track drain. Well, if you're using for example, when you're using it on cohesive soils, on soft soils, for example, the clay already have poor drainage in that sense. So you're not going to be really affecting the permeability of the clay. And the permeability of the geopolymer is very close to the permeability of clay. So you're not going to really change anything from that point of view. Obviously, when we come to do the design, drainage is something that we always look at to make sure that we don't affect the drainage system. So it's all going to be addressed in the design process to ensure that we don't affect it. But it doesn't mean that if you use this technology, you're going to need more track drainage. That's not necessarily the case, because probably you're going to be injecting below the drainage level in that sense. So you're not going to be affecting it in that, for an instance, for example. Okay.
Okay, that's fine. And there's a couple of questions then, we'll go through them in turn from Philip. Can you elaborate on the environmental impact of geopolymers? Presumably they're hydrocarbons. Is there a propensity to release hydrocarbons or other unfriendly potential hazardous substances over time?
No, we've done some environmental testing for the environmental agency via third-party consultants. So we're not the one who did the testing. So it was a third-party consultant doing it for the environmental agency. And the report finding have actually shown that the geopolymer is not going to leach or contaminate the soil, and it doesn't have any hazardous material as a byproduct when it's installed, for example. So it's quite environmentally friendly from that point of view. So it doesn't do any damage in that sense. And you can still, so when you install it, and this is something I get this question all the time, when you install this stuff, you can still excavate through it. You can still take it out, in that sense. It's not something that's going to disappear or so stiff to the point that you can't really take it out. So, and you can use that material that you've taken out as like landfill, for example, because it doesn't leach to aquifers or contaminate water or any such. So we've got extensive study on this. So happy to share the findings separately to the relevant person who's after this.
Okay. And the second part of that one, can you give some idea of the cost of track treatment and have any installations been made in the UK?
Okay, so in terms of the cost, I think it's almost similar. It has a similar answer to the micropiling solution that you've asked about, the question related to the micropiling. Obviously, it's quite different from site to site. I can't give a particular figure, but what I can tell you something is that the amount of possession that you're going to need to install this technology, for example, this solution, is far less than any other solution that you've encountered. And it can be done in discrete shifts. It can be done in midweek shifts or weekend shifts. You don't need a massive blockade to do it. You can do it discreetly in stages. So a lot of the savings will actually be, from your point of view as a client, will be related to logistics, blockage, all that. So you're not going to have, it only requires sole possession, so it's not going to disturb the operation of the network, and therefore it will reduce the amount of the cost, and also the spoil material. Can you imagine the logistical nightmare if you want to do a full-blown track renewal, for example, and you decide to kind of extend as opposed to what you would do with this technology to extend the life of your track. Full-blown track renewal will take, I don't know, few days to complete, maybe on a small sections. But with this technology, you only need one or two shifts to treat a small or a section, a similar section. So the savings can be done on direct cost, but also on indirect cost as well from that point of view.
Okay, excellent. Next question from Mike. What is the free rise density of the material used in the pile application?
Well, the free rise density, it's also, again, depending on soil condition. There's no specific answer to this. It's different from one site to site, depending on site investigation. So there's no specific answer to this. It can be anything, really, depending on the design. I mean, as a supplier, there's plenty of other suppliers. I'm sure Mike knows that very well. Plenty of other suppliers. This is really depending on the design. So we can use different types depending on what the design tells us or what the SI tells us.
Okay. Next one from Ian. How does the product perform in cohesive soils when they desiccate?
I think in my presentation, it's actually based. I've done some sensitivity analysis, and actually the amount of strength that you get on cohesive soils is actually more. So it's actually more effective as well on cohesive soils than granular. It does a good job on granular materials, but there's a big misconception about this technology or grouting overall in that sense that it's better on granular soils. It's more straightforward to design it on granular soils, but on clay soils it does, or cohesive soils, it does give quite a significant improvement that could exceed what you would get on granular soils.
Okay. And the final question from Peter: where soils have been injected, what other measures are required to prevent further washout and more void appearing? Is the injection designed to retain the remaining?
Sorry, can you repeat that question? I think you.
Okay, so I think somebody's mowing the lawn outside my house. Where soils have been injected, what other measures are required to prevent further washout and void from appearing?
Yes. So I think that's a very good question. Obviously, so for example, let's say you want to treat a particular area. Okay, let's say you've got massive voiding in the ground for a reason. Okay, I think treating the area, just little tiny area where you've got the actual problem, I think this is not effective. I think what you need to do is, and this is what we do actually when we look at the design development, we look at the underlying reasons and ensure that we treat enough in such a way that this doesn't progress further. So you kind of stop the deterioration, not just treating the symptom, trying to also kind of stop the root cause of the problem, and obviously it's also dependent on the client budget and what they're willing to go for, but we always try to recommend a solution that would kind of reduce or kind of dampen the effects of the root cause, to reduce the rate of degradation, not just treating the symptom itself. But it all comes out or gets flushed out as part of the design process.
Okay, excellent. So I suppose to close out, it's been really, really interesting, Mohamed. A different product and something that I think, with a little bit of work, there's a lot of potential use cases there, something that I found very interesting. So I think it'd be interesting to invite you back in a while and kind of go over perhaps some case studies as it develops. So you'd be very welcome to do that. And of course, as you said at the beginning, you're always welcome at Birmingham Section, so do feel free to come along to any future meetings.
Thank you very much, Richard. It's been a pleasure. Thank you. It's really interesting, and it's to see all these questions and the engagement of you guys. It's really interesting. Thank you very much for giving me the opportunity to present here.
It's our pleasure. Thank you. Thanks.
Cheers.